Okay, students, let's get started with A2 Physics, Paper 5, Question 2. So, basically, we will be covering the entire top to bottom Question 2. We will be seeing past papers of the last 5 years and we will be covering all these topics. So, let's start right away. I hope this video is less than 3 hours, but I think this will be a longer video. So, make sure you have the appropriate snacks, etc., with you. So let's look at the first thing in paper 5 question 2, that is rearranging the equation. The first thing, the first skill that you will require in paper 5 question 2 is rearranging the equation. Okay. So what do I mean by rearranging the equation? Basically, the examiner will give you a certain equation. He will say something like this. It is suggested current and resistance are related by this equation. And where E is the EMF of the cell. Perfect. And the examiner will indicate what is plotted on the y-axis and what is plotted on the x-axis. Here the examiner is saying 1 over current is plotted on the y-axis, resistance on the x-axis. You have to somehow rearrange this equation so that 1 over I is plotted on the y-axis and resistance on the x-axis. The first and foremost thing that you can do is you can write this equation as it is 3e minus es is equals to I 3r plus 2z. Perfect. This is 2z. This is not z and z. Sorry for my writing. This is 2z. Perfect. Now, first of all, you have to make sure that 1 over I is on the y-axis. So what will you do? You will take this current and divide it here. Secondly, you will take 3e minus es. You will take 3e minus es and divide it in the denominator here. Perfect. How will the equation now look like? 1 over current is equals to 3r plus 2z divided by 3e minus es. Perfect. Let's further break this up. 1 over current is equals to 3 divided by 3e minus es bracket r plus 2z divided by 3e minus es. Basically, what have I done? I have splitted the denominator in these. I have basically splitted the numerator 3r and 2z separately. Simple. Now, if I compare this equation with the equation of a line, 1 over I gets plotted on the y-axis, r is on the x-axis. Perfect. What is the gradient? You have to determine the expressions for gradient and y-intercept. What is the gradient? This 3 over 3e minus es is your gradient. So you can write it here. Your gradient is equals to what? Your gradient is equals to 3 divided by 3e minus es. Perfect. What is your y-intercept equal to? Your y-intercept is equals to 2z. This is your y-intercept. Y-intercept is equals to what? Y-intercept is equals to 2z over 3e minus es. So basically, this is how part A or the first part of question number 2 is structured. You will be given an equation, you will be told what is plotted on the y-axis, what is plotted on the x-axis. You will have to rearrange in a manner that 1 over I or the term given that is to be plotted on the y-axis is rearranged like this, and the term given on the x-axis is plotted on the x-axis. Simple. And then you will compare and find out the gradient and the y-intercept. Simple. This question is of October November paper 5 variant 1 and question 2. So let's see the marking scheme as well for this. Let me bring in the so this is the marking scheme. If you can see, you can see the gradient is 3 divided by 3e minus es. The y-intercept is 2z divided by 3e minus es. So put it in summary or to put it short in part A of question number 2, you will have to rearrange the equation. You will have to show the examiner you are plotting the same variable on the y-axis and the indicated variable on the x-axis. You will have to give the expression for the gradient and the y-intercept. Now this is basic simple algebraic manipulation. Let's try out another example. Let's try out this equation. You have to plot t on the y-axis and c on the x-axis. Perfect. Let's rearrange the equation in that manner. ln v over v naught is equals to minus t over cr. Now if you have to plot t on the y-axis, what can you do? You can take this negative and cr to the right hand side. Let's take negative and cr to the right hand side. This will become what? This will become negative r, or you can say it like this. This will become t is equals to negative r ln v over v naught. Perfect. And what is the remaining variable? C. If you see, your t is now plotted on the y-axis. This is your y-axis. Your c is now plotted on the x-axis. Simple. What is the gradient here? What is the expression for the gradient here? Negative r ln v over v naught. Let's write it here. The gradient here is equals to negative r ln v over v naught. Simple. Let's check the year. This is May June 2023 51. So let me see if I have this air open. 1 second. Yeah, here you have it. You can see that the gradient for this paper is negative r ln v over v naught. So we have also done the same thing. So now basically this is simple algebraic manipulation. You can do it. You can calculate what is the gradient, what is the y-intercept. Simple. Now let's increase the difficulty of this type of questions. How can we increase the difficulty of these types of questions? If we have ln or lg in the equation. Let's see an example. Let's see this. Let's see this question. You are given that a graph of LGT should be plotted on the y-axis and a graph of LGL should be plotted on the x-axis. Simple. So LGT should be on the y-axis, LGL should be on the x-axis. But currently in the equation you have no LGs. So first of all, what will you do? You will write the equation like this. T is equals to 2ln divided by C. If you see that you have to plot LG on the y-axis and LG on the x-axis, what will you do? Take LG on both sides. LG on both sides. Perfect. Let's take LG on both sides. LG T is equals to LG 2 over ln n divided by C. Perfect. Now, if you don't remember the rules for logs, I have pasted it here. LG of A into B is equals to what? LGA plus LGB. Simple. LG of A into B is equals to LGA plus LGB. So basically, you can split this LG into two halves, 2 over C and LG LN. You can split this into two halves. This will become what? LGT is equals to LG 2 over C plus NLGL. Simple. Let's rearrange the equation further. LGT is equals to NLGL plus LG 2 over C. Now, if you plot LGT on the y-axis, LGL on the x-axis, what will your gradient be equal to? What will your gradient be equal to? Your gradient will be equal to N. Simple. And your y-intercept will be equal to what? LG 2 over C. So let's write it here. Gradient is equals to n, and y-intercept will be equal to what? Beta, y-intercept will be equal to what? Y-intercept will be equal to LG 2 over C. Let's check whether we have gotten it correct or not. May, June 2024, paper 5, question 2. Let's see if I have that open. Yeah, you can see it here. You can examine it here that the gradient is equals to n and y-intercept is equals to lg2 over c. I am showing the marking scheme side by side so that you have some built-in confidence that you are doing this correct. Now let's move on to the third type of rearranging the equation. Let's move on to the third type of rearranging the equation. Let's say you have an equation like this. V is equals to I naught RE minus T over CR. Perfect. And you have to plot what? You have to plot ln V on the y-axis and 1 over C on the x-axis. Perfect. Let's see what can we do here. Let's see what can we do here. First and foremost, the journal rule is to write the equation again so that you have some resemblance or you feel comfortable with the equation. I naught RE minus T over CR. Perfect. Now, since you have to plot ln on the y-axis, you will take ln on both sides. Take ln on both sides. Perfect. This will become what? ln V is equals to ln I naught R E minus T over CR. Perfect. You have this entire thing inside the bracket. Now, if you don't remember the rules of ln, I have pasted it here. And this document will be available in the link in the description. ln AB is equals to what? It can be broken down into ln A plus ln B. ln AB can be broken down into what? ln A plus ln B. So let's break this up. You can say ln V is equals to ln I naught R plus ln E minus T over CR. Perfect. Let's rearrange the equation further. One more thing that you can realize is ln and E will get cancelled out because they are anti-logarithms and logarithms. ln V is equals to minus T over R 1 over C plus ln I naught R. Simple. Now, if you can analyze, ln V can be plotted on the y-axis. 1 over C can be plotted on the x-axis. Your gradient will be equal to what? Minus T over R. Your y-intercept is equals to what? ln I naught R. So you can write this here. You can write this here. You can say that the gradient is equals to what? Minus T over R. What is the y-intercept? What is the y-intercept? The y-intercept is equals to ln I naught into R. Let's see this question. This is October, November 2023. So let me, yeah, find it. I have gotten this question. Let me show you the marking scheme. In the marking scheme, if you visualize in the marking scheme, yeah, you can see it in the marking scheme that minus T over R is your gradient and ln I naught R is your y-intercept. So this marks the end of our first topic. This marks the end of our first topic that was rearranging the equation. This marks the end of the first topic that was rearranging your equation. Let's come on to the next topic that is the rules for significant figures. There are some specific rules for significant figures that you need to follow if you want to attain a good mark in paper 5 question 2. First of all non-zero digits are significant. First of all non-zero digits are significant. 6 to 3 has how many significant figures? 3. Now let's say I write something like this, 7 to 9. This also has 3 significant figures. Let's say I write something like this, 54. This has 2 significant figures. Let's say I write something like this, 8. This has 1 significant figure. And let's say I write something like this, 1, 4, 2, 3. This has 4 significant figures. So all non-zero digits are significant. All non-zero digits are significant. This is the number one rule for significant figures. Let's move on to rule number 2. Let's move on to rule number 2. Let's keep it here. In rule number 2, what is written? All zeros that are found between non-zero digits are significant. Perfect. So this 0 and this 0 that is found between non-zero digits are significant. What are the total number of significant figures here? 1, 2, 3, 4. The total number of significant figures here are 4. Let's see this. All zeros between non-zero digits are significant. So let's say you have something like this. 1 point. This is a decimal 006. This 0 and this 0 are significant because they are between non-zero digits. This is also significant. This is also significant. This is 4 significant figures. Let me give you some more examples. Let's say you have 103 written here. This is 3 significant figures. Let's say you have somewhat like this 1.203. This is 4 significant figures. Let's say you have 20703. This is 5 significant figures. Why? Because this 0, both of them are between non-zero digits and the non-zero digits are already significant. So this is 5 significant figures. Perfect. Let's move on to rule number 3. All leading zeros are not significant. Now, sir, what do you mean by leading zeros? What do you mean by leading zeros? Leading zeros are the zeros that are before a non-zero digit. Leading zeros are the zeros that are to the left of a non-zero digit. Or you can say leading zeros are the zeros that are before a non-zero digit. All leading zeros are not significant. All leading zeros are not significant. So here, all these three zeros are not significant. Only 4 and 6 is significant. You have two significant figures. Here as well, if you analyze all leading zeros, that is this one, is not significant. Only the non-zero digits are significant here. Let's say I write something like this 0009. All the leading zeros, all these three zeros are not significant. Only 9 is significant. This is one significant figure. Let's say I write something like this 0.0004. All these zeros are not significant. Only this 4 is significant. This is also one significant figure. Simple. Let's move on to the fourth rule. Let's move on to the fourth rule for significant figures. The fourth rule of significant figures states that all the trailing zeros after a decimal point are significant. All the trailing zeros. What do trailing zeros means? Zeros after a non-zero digit or zeros to the right of a non-zero digit. Basically, trailing zeros are what? You can write it here. Trailing zeros, if you want to write the definition, trailing zeros are zeros to the right of non-significant figures, are zeros to the right of non-zero digits. Simple. This is the definition of trailing zeros. All the trailing zeros to the right of the decimal place are significant. If you see here, you have two zeros to the right of the decimal place. Both of them are significant. And this is also significant. So total number of significant figures becomes what? 3. If you see here, the zeros before these zeros, the leading zeros, the zeros before a non-zero digit or zeros to the left of a non-zero digit are not significant. This 0 that is to the right of the non-zero digit, this is significant. This 5 is also significant. You have two significant figures. So basically, the crux or the summary that you need to remember for rule number 4 is that all trailing zeros after a decimal point are significant. All trailing zeros after a decimal point are significant. Now, the most important journal rule. Basically, we are studying some journal rules for significant figures. Then we will move on to the specifics. First of all, we are clearing out a journal rules for significant figures. Then we will move on to the specifics. Now, the fifth and the most important journal rule. What happens to trailing zeros without decimals? What happens to trailing zeros without decimals? Are they significant or not? Or you can say, what happens to trailing zeros at the end of a whole number? Are they significant or not? What happens to trailing zeros after a whole number? And you can say it like this as well. What happens to trailing zero without a decimal point? This is an interesting case. Now let's say you have a number like this, 1000. Whether these three zeros will be significant or not. How will we know that? How will we know that whether these three zeros of 1000 are significant or not? Very, very easy. For this, we use the uncertainties. For this, we use the uncertainties. Let's say 1000 is written like this, 1000 plus minus 100. Then 1000 is written like this, 1000 plus minus 10. Then 1000 is written like this, 1000 plus minus 1. Now, please focus on the board. Please focus on the board. You utilize uncertainties to determine whether the zeros after or trailing zeros after a whole number are significant or not. How do you do that? Just focus on the board. Let's say this is your uncertainty of 100. This is your unit, this is your 10, this is your 100. Perfect. Unit 10, 100. What is the highest place value here? The highest place value is 100. The highest place value is 100 in the uncertainty. Simple. Let's mark the place values of the actual number as well. Unit 10, 100, 1000. Perfect. The highest place value of the uncertainty is 100. Now, your actual value will have significant figures till the highest place value of the uncertainty. Let me repeat it. Let me repeat it. Your actual value will have significant figures till the highest place value of uncertainty. You can write it here. Your actual value has significant figures, till the highest place value, highest place value of uncertainty. Perfect. Now, what is the highest place value of uncertainty here? 100. So, your actual value will also have significant figures till the 100th place value. How many significant figures does this become? Two significant figures. Let's try out here. This is unit, this is tenth. The highest place value of the uncertainty is tenth. Let's write the place values of the actual value. If you write the place values of the actual value, this will become unit 10, 100, 1000. What is the highest place value of the uncertainty? 10th. So your number of significant figures will be till the 10th place value. How many significant figures do we have? 1, 2, 3. This is 3 SF. Let's do it here. This is unit. The highest place value for uncertainty is unit. Let's say this is unit 10, 100, 1000. The number of significant figures in the actual value will be till the unit place value. How many significant figures do we have here? 4 significant figures. Let's try out 2, 3 and 4 as well. Let's try out question 2, 3 and 4 as well. If you analyze 100 plus minus 10 is written. What is this? Unit 10. What is this? Unit 10, 100. What is the highest place value of the uncertainty? 10. What will be the place value till which we count the significant figures of the actual value? Till the 10th place value. This becomes 2 significant figure. Let's do the same thing for question number 3. Let's say you have 100 plus minus 1. This is unit 10, 100. Now, what is the highest place value in the uncertainty? Unit. So you will count your number of significant figures till the unit. There are 3 SF. Let's do question 4 as well. 500 plus minus 5. This is unit. This is unit 1000. The highest place value is unit. What will be the place value till which you count the significant figures of the actual value unit, because the highest place value in the uncertainty is unit. These are your 3 significant figures. Simple. I hope all the 5 rules for significant figures are clear. Now let's move on to some specifics. For paper 5. Whenever you are performing multiplication or division, the number of significant figures in the final result is the same or one more as the least number of significant figures in the raw data. Now, please remember this journal rule for multiplication and division. Whenever you are performing multiplication or division, the number of significant figures in the result is same or one more as the least number of significant figures in the raw data. Sir, what do you mean by that? Can you see we are given the frequency? How many significant figures does the frequency have? 3 SF. So the calculated value 1 over f, 1 over frequency, will either have how many significant figures? Same, that is 3 significant figures, or one more, that is 4SF. Let's calculate it. 1 divided by frequency will be equal to what? 1 divided by 528 into 10 raised to the power of 6. Can you calculate this answer? Can you guys calculate this simple answer? 1 divided by 528 into 10 raised to the power of 6. This gives you a value of 1.8939393939 into 10 raised to the power of minus 9. Obviously, you will not be writing such a big value. You will be limiting your answer till either 3 significant figures or 4 significant figures. Now, how can you limit your answer till 3 significant figures? You can only consider these 3 significant figures. 1.89 into 10 raised to the power of minus 9 is your answer till 3SF. However, if you want to write the answer till 4SF, what will you do? You will consider these first 4 digits. If you consider these first 4 digits, there is a slight thing that you have to take care of. Can you see this fifth digit? Is greater than 5. If your fifth digit is greater than or equal to 5, you will add 1 to the fourth digit. So this will become 3 plus 1. This will be 4 into 10 raised to the power of minus 9. This is your answer till 4 significant figures. Either you can write your answer till 1 significant figure or 4 significant figures. It doesn't matter. Let's see example number 3. Now, example number 3 has a slight twist. In example number 3, you have 2 raw datas, or you have 2 values through which you have to calculate the velocity square. Perfect. So if you analyze here, this d or distance is still how many significant figures? 1, 2. 2 significant figures. Perfect. This time period t is still 3 significant figures. Okay. Now, what will be the number of significant figures in velocity square? Please remember the rule. Your number of significant figures is same or one more as the least number of significant figures in the raw data. Now, if you analyze here, now this is a point that I want your undivided attention. If you analyze here, out of D and T, which one has the least number of significant figures? D. Out of D and T, which one has the least number of significant figures? Obviously D. It has 2 significant figures. So your velocity square will have either 2 or 3 significant figures. Whenever we are determining the number of significant figures for the calculated value, we always consider the significant figures. We always consider the least number of significant figures in the raw data. We always consider the least number of significant figures in the raw data. Always remember this. Whenever we are determining the number of significant figures for the calculated data, we always take the least number of significant figures in the raw data. This is what I have written in the rule as well. The number of significant figures in the result is same or one more as the least number of significant figures in the raw data. Simple. So what are the least number of significant figures in the raw data? 2SF. So your value or the number of significant figures will either be 2SF, same, or one more. Simple. Let's calculate velocity square. This will come out to be 0.030 divided by 0.0581 whole square. Can you calculate this answer? 0.030, 0.0581, and square this up. Your velocity square comes out to be this 0.266618. Now, obviously, you wouldn't write such a long answer. You will limit it to either 2SF, that will become what? 0.67. Why do I write 0.67? Because if you analyze, the third significant figure is greater than or equal to 5. If your third significant figure is greater than or equal to 5, your second significant figure will get added 1. This is your answer till 2 significant figure. However, if you want to write the answer till 3 significant figure, what will your answer become? 2.67. Why? Because the fourth significant figure is also greater than 5. You will add a 1 in the third significant figure. This is still 3SF. Simple. Is there anything that I want to tell you further? No, I guess that's it. So this is how you write till 2SF or 3SF. Or this is how you determine the number of significant figures when you are either multiplying or dividing. Let's move on to how to determine the number of significant figures when you are adding or subtracting. Very easy rule again. Whenever you are adding or subtracting, the number of decimal places in the result is the same as the least number of decimal places in the raw data. Whenever you are adding or subtracting, the number of decimal places in the final answer is the same as the least number of decimal places in the raw data. Perfect. So if you analyze here, x has how many decimal places? 1 decimal place. Y has how many decimal places? 3 decimal places. So what will be the decimal places in x plus y? Least number, it will be 1 decimal place. Let's calculate x plus y. 2.3 plus 1.946. This will come out to be what? 2.3 plus 1.946. This comes out to be 4.246 meters. Now, if you analyze, this is incorrect because how many decimal places do we have? 3. We have to give our answer till the least number of decimal places, that is 1 decimal place. The correct answer will be 4.2 meters till 1 decimal place. Simple as that. Let's try out another example. Let's say you have x as 1.9 meters or y as 1.115 meters. Now, if you analyze, x has how many decimal places? 1. Y has how many decimal places? 3. What will be x minus y? 1.9 minus 1.115. Let's calculate it. 1.9 minus 1.115. This comes out to be 0.785 meters. If you analyze, the least number of decimal places is 1. Your x minus y should also be till 1 decimal place. This will become what? 0.8 meters as your answer. Now, why did I wrote 0.8? Because the second decimal place is greater than equal to 5. Hence, the first decimal place will get 1 added. This will become 0.8 meters. Simple. Now let's move on to the rule for logarithms. How will we calculate the significant figures in logarithms? Very easy rule again. For logarithms, the number of decimal places in the final answer. For logarithms, the number of decimal places in the final answer is equal to what? Is equal to the number of significant figures in the original number. Perfect. Let's apply it. For logarithms, the number of decimal places in the final answer is the same as the number of significant figures in the original number. If you analyze here, how many significant figures do we have here? 3 significant figures. So the final answer will have 3 decimal places. Let's calculate it. LG 622 into 10 raised to the power of 6. Let's utilize the calculator. Log 622 into 10 raised to the power of 6. This comes out to be 8.7937908038. Yeah, this is a pretty large answer, but you cannot write this. You only need the first three decimal places. Why? Because your original value was still three significant figures. You will write 8.79, and since the fourth decimal place is greater than equal to 5, this will get added 1. This will become 4. This is your answer. The last rule for significant figures, the last rule that you need to get an A star or an A in physics. For anti-logarithms, the number of significant figures in the final answer. For anti-logarithms, the number of significant figures in the final answer is what? Is equal to the number of decimal places in the original number. For anti-logarithms, the number of significant figures in the final answer is the same as the number of decimal places in the original number. Now, if you analyze here, how many decimal places do we have here? 2SF. Now, if I apply, this is LGX is equals to 6.23. How to remove LG? Have we studied what is the anti-logarithm of LG? The anti-logarithm of LG is 10. If you want to remove LG, what will happen? This will become 10 raised to the power of 6.23. Whenever you have to remove LG, the number on the other side of the equation will come in the power of 10. Now, if I write this answer, 10 raised to the power of 6.23, this will become 1698243.652. Obviously, you cannot write this large of an answer. Now, your original value had two decimal places. So your final answer will have what? Two significant figures. Let's reduce this till two significant figures. This will become 1 and 7. Why? Because the third significant figure is greater than equal to 5. This will become 1, 7, 0, 0, 0, 0, 0. This is your final answer. I hope I'm correct. Two zeros. Yeah, five zeros. Perfect. Let's try it out with example number 2. In example number 2, we have ln. Now, how can we remove ln? How can we eradicate ln? Or how can we remove ln? You can say it like that. lnx is equals to 4.9. How to remove ln? What is the anti-logarithm of ln? E. Whenever you remove ln, the other side of the equation will come in the power of e, e 4.9. Let's calculate this answer. E 4.9. This comes out to be 134. This comes out to be 134.3. Obviously, you cannot write this entire answer. What are the number of decimal places in the original value? One decimal place. So your answer will be till 1SF. Let's convert it to 1SF. This will become 100. This is your answer till 1SF. So these are the 5 major rules that you need to remember for significant figures. The first rule or the first set of rules was the journal rule for significant figures. Then we moved on to significant figure rules for multiplication and division. Then we moved on to rules for significant figures while adding and subtracting. And then we saw some rules of significant figures for logarithms. And lastly, we saw rules for significant figures of anti-logarithms. Now let's try out a question. Let's try out this question. Now, if you see here, you are given, this is basically October, November 2024, paper 5, variant 1, question 2. Now, if you see here, you are given some values of resistances, you are given some values of current. You have to calculate and record the values of 1 over I. Okay. So, first of all, first and foremost thing, what can you analyze here? All the values of current are in three significant figures. So the calculated value of 1 over I will either be till three significant figures or four significant figures. Let's calculate some of the values. 1 over I for the first row will be equal to what? 1 over 194. And if you leave it like this, don't expect the examiner to give you a marks because you have conveniently ignored the table headings. This is microampere, so you will multiply it by 10 raised to the power of minus 6. Let's calculate this answer. 1 divided by 194 into 10 raised to the power of minus 6. This gives you an answer of what? This gives you an answer of 5154.6. Obviously, you will not write it like this. You will write it till three significant figures. This will become what? 5150. Let's write it here. 5150. Perfect. Let's calculate it for the second row as well. 1 over 180 into 10 raised to the power of minus 6. This comes out to be what? This comes out to be 1 over 180 into 10 raised to the power of 6 is comes out to be 5555.5. You can restrict it till three significant figures. This will become what? 5560. Perfect. Let's write it here. 5560. Let's do it for the third one as well. 1 over 172 into 10 raised to the power of minus 6. This comes out to be 1 over 172 into 10 raised to the power of 6. This comes out to be 5813. Till three significant figures, it will become what? 5810. So 5810. Let's do it with 160 as well. 160 into 10 raised to the power of minus 3. Let's do it here. 160. This comes out to be 6250. This is already in three significant figures. 6250. Perfect. Let's do it for the fourth and fifth column as well. 1 divided by 150 into 10 raised to the power of minus 6. This becomes what? This comes 1 divided by 150 into 10 raised to the power of minus 6 comes out to be 6666, which can be converted into 6670. Perfect. 6670. Let's do it for the last one. 1 divided by 144 into 10 raised to the power of minus 6. This comes out to be 6940. Simple calculation. This is how you will fill the table. You have to make sure that the number of significant figures during multiplying or dividing is either same or one more. Here we were dividing. So the number of significant figures were either same or one more than the actual value के significant figures. Simple. So these are your data that you have calculated. This paper is October, November 2024, paper 5, variant 1. Let's check out whether we have calculated correct or not. I think, yeah, here we have it. 5150, 5560, 5810, 6250, 6670, 6940. We are on the correct path. Let's move ahead. Let's try out another table. Now let's try this one out as well. You are given some values of theta, 1 over sine theta square, d and du square. You have to basically calculate and record the values of du square. Perfect. This is October, November, paper 5, variant 2, question 2. So right off the bat, if you analyze, all the values of d are till three significant figures, and this is multiplying d by d. So basically d square can be written as what? D multiplied by d. So this is the case of multiplication and division. So your number of significant figures will remain till 3 or 4 SF. Perfect. So your initial d is 24.8. D square will become what? 24.8 whole square. This will become what? 24.8 whole square. This comes out to be 615.04. Obviously, you will write it till three significant figures. 615 is your answer. Let's do it for the second row. 21.4 whole square. This will come out to be what? 21.4 whole square. This comes out to be 457.96. If you convert it till three significant figures, this will become 4, 5, and 8 because the fourth number is greater than equal to 5. 4, 5, 8. Perfect. Let's do it for the next one. Next one is 17.1 whole square. 17.1 whole square is equals to what? 292. 292.41. If you convert it till three significant figures, this is 292. Perfect. Let's do it for 14.7 square. This will come out to be 14.7 square comes out to be 216.09. If till three significant figures, this is 216. Let's write it here, 216. Let's do it for 12.9 square. 12.9 square will be equal to what? 12.9 square is equals to 166.41. This will be equal to 166. Till three significant figures, 11.8 whole square is equals to 139. Perfect. So this is how will you calculate the values of d square to the appropriate number of significant figures. Let's check it out as well whether we are correct or not. Let's check it out as well whether we are correct or not. This is October November paper 5 variant 2. So if I see here, yeah, this is the one. 615,458,292. I guess we are correct. 216 is also correct. 166 is also correct. 139 is also correct. So yeah, we are going good up till now. Now here I have already filled the table just to save some time. Now there is a unique thing happening here in May, June 2023, paper 5, variant 2, question 2. You had to calculate the volume and the formula of volume was given. And there are two raw datas. There are two raw datas. D, value of D and value of H. There are two raw datas, value of D and value of H. How many significant figures does D has? 3. How many significant figures does H has? How many significant figures does H have? 3. So I have written my final answers till 3 significant figures, all of them. Let's keep on filling the rest of them. Basically, the logic remains same. Okay, so a little bit of commentary here. If you can see, your D is in two significant figures. So your final answers of time will either be in two significant figures or three significant figures. I have kept all the answer till two significant figures. Now, a problem that you will face in examination, I am damn sure of, is in this first row. When you calculate the time period here, you will say D into the time base supply. You will see there D into the time base supply. D is 1.4 multiplied by the time base supply. That is 5. Your answer will come out to be 7. And you will unknowingly write 7 here. This will cause your answer to be incorrect because 7 is still one significant figure. How can you increase the number of significant figures of 7? By adding a decimal point and a 0 here. This now becomes two significant figures without changing the actual value. Now here as well a little bit of commentary. If you can see, the first column was pretty easy to fill. You were given your capital M, you are given different small m's, you just add them and calculate the values. For the second column, as you can see, all the V values are till three significant figures. So your calculated values can either be till three significant figures or four significant figures. The calculation is pretty easy. Just input 1 over the value that you are given in the row. 1 over 4.42, you will get this answer. 1 over 3.92, you will get 0.255 as your answer. Obviously, you can check this in the marking scheme as well. Just a little bit of commentary here as well. You can see this is October, November 2022, paper 5, variant 1, question 2. I have just calculated the values. The problem that you will face here is if I put 1 over 22, if I put 1 divided by 22, my answer will come out to be 0.54 4545, sorry, 0.04545 and keep on continuing 45. Now, there are two things that you need to observe here. First of all, you have to observe that R is still two significant figures. So, your 1 over R will either be till two significant figures or three significant figures. But you also have to realize you have to give your answer till 10 raised to the power of minus 3. What will you do? 1 decimal place, 2 decimal place, 3 decimal place. Your answer will come out to be 45.4 into 10 raised to the power of minus 3. I have preferred to give my answer till two significant figures. This will be your answer. No need to write 10 raised to the power of minus 3 here because it is already incorporated into the table. Let's fill the other tables as well. Again, a little bit of commentary here. This is May, June 2023, paper 5, paper 5, variant 1, question 2. Now, if you realize your CP and CQ values are both till two significant figures. They are both till two significant figures. So your calculated value of C can either be till two significant figures or three significant figures. I have preferred two significant figures and these are my values. I have utilized this formula to calculate C. Now the time part is a bit tricky. This is three significant figures. This is three significant figures as well. Your calculated value of time will also be till three significant figures, or you can say one decimal place. Why do I say that? Because this capital T is your time average and this is equals to what? T1 plus T2 divided by 2. Whenever you are adding things, what do you have to remember? The final value is to the least number of decimal places. What are the least number of decimal places here? One decimal place is the least number of decimal place here. One decimal place is the least number of decimal place here. So your final answer will also contain one decimal place throughout. Simple as that. This is the rule for significant figures in addition and subtraction. You can go over the video again if you have forgotten this. Now again a little bit of commentary here. This is May June 2024 paper 5 question 2 variant 2. For LGL, can you realize the first three values have what? They have two significant figures. So the LG of the first three values will be till two decimal places as you can see here. The last three L the last three values of L have three significant figures. So the last three values of LGL will have three decimal places. You can also see T. All the values of T have two significant figures. So all the values of LGT have two decimal places. Simple as that, nothing complicated here. So yeah, a little bit of commentary here. As you can see, this is October, November 2023, paper 5, variant 2 and question 2. So basically, in the first two capacitance values, this is still two significant figures, this is still two significant figures. So your calculated value of capacitance will also be till two significant figures or three significant figures. I have given the values till two significant figures. Simple. Let's move on to the fourth column. If you see the values of voltage are given till how many significant figures? Three significant figures. So LNV will be till how many decimal places? Three decimal places. Do you remember logarithms ka rule? The number of significant figures in the original number is equals to the number of decimal places in the calculated value. Now let's move on to uncertainties. How to calculate the uncertainties that the examiner is telling us. So I have divided the uncertainties into some types. Let me show you. Yeah. There are five major types of uncertainties that can come in your examination. There are five major types of uncertainties that can come in your examination. Let's first of all start by calculating uncertainty when the variable is either multiplying or dividing. Let's do that. Let's first of all calculate the uncertainty when the variable is either multiplying or dividing. Here you have it. Here you can see that current is getting divided. Here you can see that current is getting divided. So this is a basic case of calculating uncertainty when variables are multiplying or dividing. Okay. So how will you calculate the uncertainty here? How will you calculate the uncertainty in 1 over V? How are you going to calculate the uncertainty in 1 over V as instructed in the question? Calculate the absolute uncertainties in 1 over V. You have to realize one very simple fact. What is 1 over I made of? 1 over I is made of a variable known as current or I. Okay. So you can say that the absolute uncertainty in 1 over I divided by 1 over I is equals to what? Absolute uncertainty of current divided by the actual value of current. So here you can write a key point in multiplication or division, fractional uncertainties add up. Fractional uncertainties add up. Simple. So here you can see fraction uncertainties add up. Simple. The absolute uncertainty of 1 over I divided by 1 over I is equals to the absolute uncertainty of current divided by the current. Simple. Now, what I have found helpful in the examination is to rearrange the formula and create a journal formula. Now, what I have found helpful in the examination is not to do this again and again. Instead, rearrange the formula and create a journal formula for every question. The journal formula for every question will be different. The absolute uncertainty in 1 over I is equals to what? 1 over I multiplied by change absolute uncertainty in I divided by I. Perfect. Now, this is the journal formula. You can apply it to all the rows and calculate the absolute uncertainty. Okay, let's start applying. Since this is our first question, let's start applying. For the first row, your 1 over I value is, for the first row, your 1 over I value is 5150. Your absolute uncertainty of I is 2. Your value of current is 194. You can just create a fraction in the calculator and just keep on changing the values. 5150 into 2 divided by 194. Simple. This comes out to be 53.09. But now here I have to tell you guys one thing. Here I have to tell you guys a very basic rule. Uncertainties, uncertainties, you can also write it as well. Uncertainties are always are always given to one significant figures. Uncertainties are always written to one significant figures, or you can say uncertainties are always given to one significant figure. Simple. So 53.09. If I make this as one significant figure, what will it become? We will only take this first figure. 50 is your answer. Plus minus 50 is your first uncertainty. Now, I think we are short on a space. So, what we are going to do is we are going to minimize this thoda sa. I hope you guys have taken a screenshot of this. Let's keep it here. Now, let's calculate the uncertainty of the second row. Let's calculate the uncertainty of the second row so that you get into the habit of this. What is 1 over I? What is 1 over I for the second row? 5560. Perfect. What is the absolute uncertainty of current for the second row? Which row I am solving? I am solving this wali row. What is the absolute uncertainty in current? 2. What is the value of current? 180. Can I calculate this? Yeah. Let's just change the values in the fraction. 194 gets 180 and 5150 becomes 5560. I am just telling you guys so that you know how to do it in the calculator. This comes out to be 61.7. Again, you have to give uncertainty. Still one significant figure. This will become 60 plus minus 60. Simple. Let's do it for the third row. Absolute uncertainty in 1 over I is equals to what? The actual value of 1 over I, 5810, multiplied by the absolute uncertainty in current divided by the actual value of current. Let's just change the values. 172 divided by 5810. Simple. 1 second. The answer comes out to be 67.5. The answer here comes out to be 67.5. If I round 67.5 to one significant figure, if you analyze, the second value is greater than or equal to 5. So we will add 1 here. This will become 70. Simple. So you can write plus minus 70. Simple. Now the last part. The last part. 6250 into 2 divided by 160, or the fourth row you can say. The uncertainty for the fourth row will be equal to what? Will be equal to 6250 multiplied by 2 divided by 160. What does this answer comes out to be? This answer comes out to be 78.1, which is equals to what? Which is equals to 80 plus minus 80. Now again we are short on space, so I'm going to do a simple trick here. I'm going to minimize this, nothing magical about it. I will put it here, perfect. Or you can say I can put it here so that this space gets empty. Let's put it here. 1 second. Yeah, let's calculate the uncertainty for the fourth row. You can say that absolute uncertainty in 1 over I is equals to what? 1 over I, that is 6670, multiplied by the uncertainty in current, that is 2, divided by the value of current. Simple, calculate this. 6670. 1 second. 6670 multiplied by 2 divided by 150. This answer comes out to be 88.9. This answer comes out to be 88.9, which is roughly equal to 90. If written to one significant figure, 90 is your answer here. The last uncertainty. Absolute uncertainty in 1 over I is equals to 6940 into 2 divided by 144. Simple. 2 divided by 144. 6940. Perfect. This comes out to be what? 96.38. If we convert this to one significant figures, can you see the second digit is greater than equal to 5? So we will add a 1 here. This will become what? 100 as your uncertainty. Let's check this out as well. Why are you guys believing me? Let's check this out in the marking scheme as well. This is October November 2024, paper 5, variant 1, question 2. If I see here, yeah, this is the one. So if you see, the examiner has given you a range of uncertainties, and this will be a regular occurrence. Examiner will not give you the uncertainty for every row. It is very rare. It is very, very rare that the examiner writes uncertainties here. It is very, very rare that the examiner puts in the uncertainty in every row. Instead, the examiner will give you a range of uncertainty. Let's see where is a range. We can see here this is a range of uncertainties from plus minus 50 to plus minus 100. This should be a range of uncertainty. And luckily, we have these uncertainties here from 50 to 100 plus minus. Yeah, that's correct. We have done this one correctly. Let's move on to a more difficult one. Let's see this one. This paper is October November, paper 5, variant 2, question 2. Perfect. Now here you are given the values of d. You had to calculate d square. We had easily done that. Now we have to also calculate the absolute uncertainties in d square. We have to calculate the absolute uncertainties in d square. If you notice, this is a typical case of multiplication. If you notice, this is a typical case of multiplication. Yeah. Whenever we were multiplying or dividing, I told you to remember one rule. What was that rule? Uncertainties, or during multiplication or division, fractional uncertainties add up. This is the rule that I told you guys. So here if you look, what can we do here? Absolute uncertainty in d square divided by the value of d square is equals to what? Absolute uncertainty of d divided by the value of d. But you have forgotten a very important thing that was taught in AS. If your variable has a power, let's say square, this will get multiplied with the fractional uncertainty. D square is made up of a square of d. So the power will get multiplied with the fractional uncertainty. Can I rearrange this formula to make absolute uncertainty of d square the subject? Yeah. 2d square multiplied by absolute uncertainty of d divided by d. This is your journal formula that we will be utilizing throughout the calculations for this question. Now, let's start. Let's start with it. So first of all, what is du square? 615. For the first row, what is du square? 615. Perfect. 2 into 615. Perfect. What is the absolute uncertainty in D? 0.2. What is the value of D? 24.8. Perfect. Can we calculate this answer? Yeah. 2 into 615 into zero point 0.2 divided by 24.8. This gives you an answer of what? This gives you an answer of, where is the cursor? This gives you an answer of 9.91. If I round it off till one significant figure, this will become 10. So you can write it here plus minus 10. Perfect. Let's do it for 458. The absolute uncertainty of d square is equal to what? 2 into 458 into what is your absolute uncertainty in d? 0.2 divided by the value of d, that is 21.4. Can we calculate this answer? Yeah. Very, very easy to calculate. 21.4, 0.2 multiplied by 458 into 2. Yeah. So this comes out to be 8.56. This comes out to be 8.56, which can be roughly equal to 9 if converted to one significant figures. Why? Sir, why do you say that? Because if you see the second figure is greater than equal to 5, so you will add a 1 here. The value till one significant figure will be 9. So let's write it here plus minus 9. Now again, I am short on space here. So what I will do is I can minimize this and keep it on the right hand side. Perfect. Let's do it for the third row. For the third row, the absolute uncertainty in du square is equal to what? 2 into du square, that is 292, multiplied by the absolute uncertainty, that is 0.2, divided by the value of d, that is 17.1. Let's calculate this. 2 into 292, 292, perfect, divided by 17.1. 17.1. This gives you a value of what? 6.8. This gives you a value of what? 6.83. If I convert this to one significant figure, this will become 7. So you can write here plus minus 7. Simple. Let's do it for the fourth row as well. Absolute uncertainty of du square is equal to what? 2 into 216 into 0.2 divided by 14.7. Can we calculate this? Yeah. Very, very easy. 2 into 216 divided by what? Divided by 14.7. This comes out to be what? 5.87. This comes out to be 5.87, which will roughly be equal to what? 6 if converted to one significant figures. Let's do the fifth row as well. The absolute uncertainty in d square is equal to what? 2 into 166 into 0.2 divided by 12.9. Let's do that. This will be 12.9 and the above value will be 166. This comes out to be what? 5.14. 5.14 if converted till one significant figure, this will become 5 plus minus 5. Now the last row as well. We can do the last row as well. I am just taking some space here. The absolute uncertainty in d square is equal to what? 2 into 139 into 0.2 divided by 11.8. Obviously, you can do all of this and calculate it directly. I am just writing it down so that you know how the process is working. This comes out to be 4.7. This comes out to be 4.7, which is roughly equal to 5 again. So now let's check out the uncertainties ka table again, whether we are correct or not. This is October, November 2024, paper 5, variant 2. So I think we have it here, yeah. So yeah, if you see it here, the examiner is telling us that the uncertainty in du square can range from 10 to 5. Yeah, our uncertainties are also ranging from 10 to 5. You can see it here. 10, 9, 7, 6, 5, 5. Correct. Let's further move ahead. Now here we also have a multiplication or division ka scenario. But this is a very hidden sort of scenario. Why? Because we have an under root here. Now let's see this question as well. This is also a typical scenario of multiplication and division. If you analyze, what is this? What is under root 1 over h? This is equals to what? 1 over h power half. Simple. So let's write it here. Absolute uncertainty of 1 over h divided by the value of 1 over h is equals to what? Is equals to the absolute uncertainty of h divided by the value of h. But you are going to multiply this by the power of the variable, that is half. You are going to multiply this by the power of the variable, that is half. What will your final formula become? Your final formula will be absolute uncertainty in 1 over h is equals to what? Is equals to absolute uncertainty of h divided by 2h multiplied by what? Under root 1 over h. Simple. This is your formula that you will be using throughout. And see how simple this has become. Very, very easy. Just plug and play. Now you can put this in the calculator and directly calculate the values of all 6 rows. But I will do it manually so that you guys know what is happening behind the scenes. So absolute uncertainty of 1 over h is equals to what? Absolute uncertainty of h, that is 0.2, divided by 2 into h, that is 21. Perfect. Multiplied by the value of 1 over h, that is 0.218. Okay, so let's create a fraction for this. 0.2 divided by 2 into 21. Okay, into 0.218. This comes out to be okay. We have a answer here. This comes out to be 0.0010. You want to make it till one significant figure, so you will just write 0.001. So you can write it here plus minus 0.001. Simple. Let's calculate it for the second row. Absolute uncertainty in 1 over h is equals to what? 0.2 divided by 2 into 17.8. Perfect. Into 0.237. Let's change the values a bit. I have just created a fraction in the calculator. I wish I could show you guys. I have just created a fraction in the calculator and I'm just changing the values. That's the reason why I am able to do this so quickly. So this comes out to be what? This comes out to be 0.0013. Now if we round it off till one significant figure, this will be 0.001. So you can write it here 0.001. Perfect. Let's do it for the third one. Absolute uncertainty in 1 over h is equals to what? It is equals to 0.2 divided by 2 into 16.2 into 0.248. Can you calculate this answer? Yeah, very, very easy. 248 gets in the numerator and divide it by 2 multiplied by 16.2. This gives you an answer of 0.0015. Now here we have a problem. This is 0.0015. If I want to convert it till one significant figure, till here, can you realize this 5 is greater than or equal to 5? So you will add 1 here. This will become what? 0.002. So you can write it here. The absolute uncertainty here is 0.002. Simple. Now let's minimize all of this and do the working for the remaining 3 rows. Let's do the working for the remaining 3 rows. So if you see the fourth row, the absolute uncertainty in under root 1 over h is equals to what? It is equals to the absolute uncertainty in h, that is 0.2, divided by 2 into h, that is 14.6, multiplied by 1 over h, that is 0.262. Simple as that. Let's calculate this value. Let's calculate this value. Oh, I have somehow erased the fraction. 14.6 multiplied by 0.262. This comes out to be this comes out to be 0.0017. Again, this will be converted to what? This will be converted to 0.002. Perfect. Write it here, 0.002. Let's do it for the fifth row. Absolute uncertainty in 1 over h is equals to what? 0.2 divided by 2 into 12.6 multiplied by 0.282. What will this answer come out to be? 282, and the denominator, may we change it to 12.6. This comes out to be what? This comes out to be 0.0022, which is equals to 0.002. Simple. So you can write it here, 0.002. Simple. Let's do it for the third row. Absolute uncertainty of 1 over h is equals to what? 0.2 divided by 2 into 10.2 multiplied by 0.313. What will your answer come out to be? Let's check that out. 313 divided by 2 into 10.2. This comes out to be what? This comes out to be 0.003, which will give you an uncertainty of what? 0.003. Perfect. Let's write it here and we will check this in the marking scheme. This is October November 2023, paper 5, variant 1, question 2. Let's see in the marking scheme whether we are correct or not. I think this is the paper. Yeah, you can see your uncertainty should range from 0.01 till 0.003. Simple. So yeah, this is correct. This question was correct. Let's move on to the next one. Now let's see this. This one is a bit interesting. I will tell you the method and hopefully we will fill half of the table, half I will fill it on myself to save some time. So if you see how was volume calculated, volume was calculated using this formula, pi du square h over 4. Perfect. So now if you have to calculate the absolute uncertainty in volume, what will you do? You will say the absolute uncertainty in volume divided by the volume is equals to what? We will ignore the constant such as pi over 4. Always remember, whenever you are doing the calculations for uncertainties, constants such as pi over 4, 64 pi, 2 pi gets ignored. How will you write d square? You will say 2 times the absolute uncertainty in d divided by d plus the absolute uncertainty in h divided by h. Why have I written a 2 here? Because d is squared. Okay, so can you create a general formula here? Yeah. Absolute uncertainty of v is equals to V multiplied by 2 times absolute uncertainty of D divided by D plus absolute uncertainty of H divided by H. Perfect. This is the journal formula that you will be inputting in the calculator, or these are the fractions that you will be creating in the calculator. Now just plug and play. Now just plug and play. So now if you realize for the first row, what is your volume? For the first row, what is your volume? Your volume is 3.81. Perfect. And what is your absolute uncertainty in D? 0.1. Perfect. So you can write it here. 2 into 0.1 divided by what is the actual value of D? 27.9. 27.9. Perfect. Plus, what is the absolute uncertainty in H? 0.1. Perfect. Divided by 62.4. Let's calculate this answer. Let's calculate this answer. What I can do is I can 3.81 into create a fraction 2 into zero point 0.1 divided by 27.9. Perfect. Plus 0.1 divided by 62.4. What will your answer come out to be? Your answer comes out to be somewhat like this. Your answer comes out to be 0.033. Now you will have to round it off till one significant figure. You will have to round it off till one significant figure. This will become what? 0.03. Perfect. So the first uncertainty is 0.03. Let's do it for the second row as well. Let's do it for the second row as well. What will we do? The absolute uncertainty in V is equals to what? 3.99 multiplied by 0.2. I have multiplied 2 into 0.1 together divided by 27.9. These values will remain same because the value of D is remaining same. Plus 0.1 divided by 65.2. Let's calculate this answer. So you will have to change this zero point 0.1 divided by 65.2. Perfect. And if I change this, this will be 3.99. The answer comes out to be 0.034. Again, till one significant figure, this will become 0.03. So let's write it here 0.03. Perfect. Let's do it for all the four rows as well. Let me do it with some commentary as well because I think you will be needing some help here. So let's do it for the third row as well. The absolute uncertainty in volume is equals to 4.16. 2 into absolute uncertainty in D was what? 0.2 divided by 27.9. Perfect. Plus absolute uncertainty of H is 0.1 divided by 68.1. What will your answer come out to be? Let's calculate that. This is 4.16. Perfect. And if you come here and rearrange this value, this will be 68.1. This gives you an answer of 0.035. Now, this is interesting. Since the third decimal place is greater than or equal to 5, we will add a 1 here. This will become what? 0.04. Simple, write it here. 0.04. Let's do it for the fourth row. Absolute uncertainty in volume is equals to what? 4.33. Perfect. 0.2 divided by 27.9. Perfect. Plus, what is the absolute uncertainty in H? 0.1 divided by 70.9. Can you calculate this answer? Yeah, very, very easy. Let's change this one. 70.9 and this is 4.33. Your absolute uncertainty comes out to be 0.037, which is again equal to 0.04 if we do it till one significant figure. Simple. Now let's do it for the fifth row as well. Let's do it for the fifth row as well. So let's do it here. Absolute uncertainty in volume is equals to what? 4.48. Perfect. Into 0.2 divided by 27.9. Perfect. Plus 0.1 divided by what? 73.3. Let's calculate this answer. This will be 4.48. Perfect. Divided by, change the value here. This will be 73.3. This comes out to be what? 0.038, which is again equal to 0.04. Simple. Let's do it for the last one. Let's do it for the last one. I think we have some space here. The absolute uncertainty in volume will be equal to what? The absolute uncertainty in volume will be equal to what? Let's do it here. Let's not. The absolute uncertainty in volume will be 4.65 multiplied by 0.2 divided by 27.9 plus 0.1 divided by 76.1. If I get all of these values correct, I will be really, really happy. Let's see. It is quite a lot of hard work here. 4.65 divided by 0.1. Okay, so the answer to this is 0.039 which is roughly equal to 0.04. Let's write it here, plus minus 0.04. Let's check it out in the marking scheme. This is May June 2023, paper 5, variant 2. So let's check in the marking scheme here. May June 2000 and we have it here. So if you analyze here, you can see here, luckily we are given the uncertainties in the column, plus minus 0.03, plus minus 0.03, and the last four are 0.04. This is what our answer tells us as well, plus minus 0.03, plus minus 0.03, and the rest are 0.04. Okay, so let's move on to the topic of how to calculate uncertainties when the variables are adding or subtracting. This is a prime example of such a question. This is May June 2021, paper 5, variant 1, question 2. Here we had to calculate the absolute uncertainties in what? Capital M plus small m. We had to calculate the absolute uncertainties in two variables that were adding. So always remember this thing. Always remember this thing. Absolute uncertainties, absolute uncertainties, uncertainties. Remember this key point. You can write it in your notes as well. Absolute uncertainties get added up during addition or subtraction. Now this is a very simple rule, but let's investigate. What does this actually mean? Absolute uncertainties get added up during addition or subtraction. Perfect. So, what do I mean by that? Let's put the key point here, somewhere here. Yeah. Now I have to calculate the uncertainty or the absolute uncertainty in capital M plus small m. If you can see, the two variables are getting added up. The two variables are getting added up. By that, what do I mean? If you want to calculate the absolute uncertainty of the entire thing, that is capital M plus small n, you will basically add the absolute uncertainties of the two variables. Please, please, please remember this golden rule. Whenever you have to calculate absolute uncertainties and your variables are adding or subtracting, what do? You add the absolute uncertainties of the individual variables. Simple. Let me repeat it again. Whenever you have to calculate the uncertainties and variables are adding or subtracting, you add the absolute uncertainties of the given variables. Simple. Now here you had to calculate the absolute uncertainty in capital M plus small m. What will you do? You will add the absolute uncertainty of capital M plus the absolute uncertainty of small m. Okay. So now, first of all, how can you calculate the absolute uncertainty in capital M? Can you realize that M has a 5% error, 5% of percentage uncertainty? So you can say capital absolute uncertainty in capital M divided by capital M multiplied by 100 is equals to 5. This is the percentage uncertainty. Perfect. What is capital M? 330. Absolute uncertainty in M divided by 330 is equals to 0.05. What will your absolute uncertainty come out to be? Yeah, let's calculate it. What will your absolute uncertainty come out to be? 16.5. Your absolute uncertainty in capital M comes out to be 16.5 grams. Simple. And this will remain constant throughout. This will remain constant throughout. Why? Because the value of capital M is remaining constant throughout. What is changing? What is changing? The value of a small m. And if you realize m or a small m also has a percentage uncertainty of 5%. If you realize a small m also has a percentage uncertainty of 5%. So let's do the calculation for the first row. Let's do the calculations for the first row. Perfect. You have already calculated the absolute uncertainty in capital M. Let's put in a black box here. Now for the first row, how will you calculate the absolute uncertainty in a small m? Very easy. Absolute uncertainty of a small m divided by m multiplied by 100 is equals to 0.05, is equals to 5, sorry, because this is 5% of percentage uncertainty. How can you rearrange this formula? Absolute uncertainty in a small m is equals to what? 0.05 into the mass, that is m. This is your journal formula now. This is your journal formula now. You will utilize this formula to calculate the absolute uncertainty in a small m for all the rows. Okay. Now let's analyze the first row. Let's analyze the first row. You have to calculate the absolute uncertainty in capital M plus a small m. You know that the absolute uncertainty in capital M is 16.5. Perfect. How will you calculate the absolute uncertainty in a small m? 0.05 multiplied by the value of m, that is 50. This comes out to be what? Let's calculate it. 16.5 into 0.05 into 50. This gives you an answer of 41.25. This gives you an answer of 41.25. One second, not 41.25. My bad here. Yeah, this gives you an answer of 19. Sorry, my bad. This gives you an answer of 19. And if you convert 19 to one significant figure, this will become 20. So you will write plus minus 20 here. Let's do it for the second row as well. Absolute uncertainty in capital M plus a small m will be equal to what? Absolute uncertainty of capital M plus the absolute uncertainty of a small m. This time the value of m is 150. So in place of 50, right? 150. And now let's calculate the answer. This comes out to be 24. Again, if I round off 24 to one significant figure, it becomes 20. Simple. Let's do it for the third row. Absolute uncertainty in capital M plus a small m is equals to what? 16.5 plus 0.05 into the value of a small m, that is 250. Can you calculate this? Yes. One second. 16. For some reason, I have erased the thing. Apologies. This comes out to be 29. And if I round off 29 till one significant figure, it will become 30. Simple. Let's do it for the fourth row as well. Absolute uncertainty in capital M plus a small m is equals to what? 16.5 plus 0.05 into what is the value of a small m now? 350. Perfect. I write it down, 350. Oh, again. I am cursing myself right now. Again, I have done the same mistake. 34 grams is your absolute uncertainty, rounded off till one significant figure is 30. Simple. So your absolute uncertainty becomes 30. Let's write plus minus 30 here. Perfect. Let's do it for the fifth row. Absolute uncertainty in capital M plus a small m is equals to what? 16.5 plus 0.05 into 500. What will your answer come out to be now? Thankfully, I haven't erased the sum in the calculator. This comes out to be 41.5, which is rounded off to 40 grams. Perfect. Let's do it for the last one. Absolute uncertainty in capital M plus a small m is equals to the absolute uncertainty of capital M plus the absolute uncertainty of a small m, that is 0.05 into 600 this time. So let's calculate this. This comes out to be 46.5. This comes out to be 46.5, which rounded off to one significant figure is 50 grams. Let's check the marking scheme as well. So this paper is May, June 2021. Okay, let me see. I have opened all the papers up. One second. No, not this one. Not this one. Not this one as well. Where is May, June 2021? I hope I find it. Yeah, you can see this one here. You can see that the absolute uncertainties in capital M plus a small m can range from 20 till a value of 50. So we are correct. We have done it correct. Your absolute uncertainties can range from 20 to a value of 50. Simple. We have done this very, very correctly. So the important key point to remember here, The important key point to remember here is when variables are getting added up, when variables are getting added up, their absolute uncertainties also get added up. When variables are getting subtracted, their absolute uncertainties also get subtracted. This is the simple golden rule that you need to remember. Absolute uncertainties get added up during addition or subtraction. Simple. Let's further move ahead. Now let's see the scenario when you are given percentage uncertainties. How will you calculate the uncertainties if you are only given the percentage uncertainty? See here, यहाँ पे you have this written. Each resistor value has a percentage uncertainty of 5%. Perfect. Each resistance value has a percentage uncertainty of 5%. How are you going to calculate the absolute uncertainties in 1 over R? How are you going to calculate the absolute uncertainties in 1 over R? Very, very easy. Very easy. You have to understand that 1 over R is what? 1 over R is a division. So in divisions, do you remember what used to happen? In divisions, what used to happen? Absolute uncertainty of 1 over R divided by 1 over R is equals to what? Absolute uncertainty of R divided by the value of R. Perfect. Now, if, see, here you have to apply some basic logic, Now, if your percentage uncertainty of R is 5%, what does this mean? This means absolute uncertainty of R divided by R multiplied by 100 is equals to 5. If I want this variable, absolute uncertainty of R divided by R, what will that be equal to? Absolute uncertainty of R divided by R will be equal to 0.05. Unknowingly, you have formulated an equation. Absolute uncertainty in 1 over R is equals to 1 over R multiplied by what is this value? This value is 0.05. Simple. This is your journal formula which you will utilize to calculate all the absolute uncertainties in 1 over R. Simple. Let's utilize it. Let's minimize these things so that we have some space. Yeah, I think this much space will be enough. Let's do it for the first row. Absolute uncertainty in 1 over R is equals to 45. That is the value of 1 over R multiplied by 0.05. This comes out to be what? 45 into 0.05. This comes out to be 2.25. If I round it off till one significant figure, it will become 2. Perfect. Let's do it for 37. Now you can just put this in the calculator. 37 multiplied by, let me do it so that you realize what am I doing. 37 into 0.05 into, this will give you an answer of 1.85. Again, if I round it off till one significant figure, it also becomes 2. Now let's calculate it for the third row. In the third row, we will multiply 30 by what? 0.05. What will your answer come out to be? Let's do it. If I multiply 30 by 0.05, this comes out to be 1.5. Again, this has a absolute uncertainty of 2. Let's do it for the fourth row. Absolute uncertainty in 1 over R is equals to 26 into 0.05. What will this answer come out to be? Let's calculate it. 26 into 0.05, this comes out to be 1.3. If I round 1.3 to one significant figure, it comes out to be 1. Perfect. Now the absolute uncertainty in 1 over R is equals to 21 into 0.05. What will this answer come out to be? 21 into 0.05. This comes out to be 1.05. It is equals to 1. Perfect. Now let's do it for 19 as well. I think I should write 19 as well just to maintain symmetry. Absolute uncertainty in 1 over R is equals to what? Is equals to 19 into 0.05. This is equals to 0.95, which again rounded off to one significant figure is 1. Let's see the year of this question. This is October, November, paper 5, variant 1, question 2. And let's see whether we have gotten it correct or not. October, November 2000 and we have this here. if you analyze, this is written here. Your absolute uncertainties will range from plus minus 2 till plus minus 1, and this is what a range is coming out to be. Simple. You can see here from 2 to 1. Perfect. Let's further move ahead. Okay, now let's move on to a unique style of questions that paper 5 sometime asks us. That is calculating uncertainty using the mean method. That is calculating uncertainty using the mean method. So if I give you a brief overview of the experiment that is happening here, if I give you a brief overview of the experiment that is happening here is we are taking two values of time, t1, t2. We are averaging out to calculate the mean time. Now always remember, whenever you are calculating a mean time or an average time, what happens to your uncertainty? How will you calculate the uncertainty when you are calculating an average time or a mean time? Now, see, this is different. This is different to the addition or subtraction scenario that we studied. Why? Because when we studied the addition and subtraction scenario, there were two different variables, capital M and a small m. There were two different variables. Here, in the mean method, you will have the same variable that you are measuring twice and you will be calculating the average. Now, whenever you are calculating the average or the mean, there is a specific way to calculate uncertainties. There is a specific way to calculate uncertainties. How do you do that? The absolute uncertainty in capital T will be equal to what? T maximum minus T minimum divided by 2. This will always be the case whenever you are taking average of same variables. ठीक है, same variables का whenever you are taking average, you will apply this formula to calculate absolute uncertainty. Perfect. Now let's do it for the first row. Let's do it for the first row. What is the maximum time? 14.5. What is the minimum time? 12.9 divided by 2. Can you calculate this answer? 14.5 minus 12.9 divided by 2. This gives you an answer of 0.8. This will be plus minus 0.8. Perfect. Let's do it for the second row. Absolute uncertainty in time is equals to what? 21.1 minus 19.7 divided by 2. This will give you an answer of what? Let's put it here. 21.1 minus 19.7 divided by 2. This gives you an answer of 0.7. I think I will have to minimize things as well. And I will have to take control of my writing as well. It is getting too big. Now let's do it for the third row as well. Okay, let's write it here, plus minus 0.7. Now let's do it for the third row as well. What is the maximum time? 24.9. What is the minimum time? 23.7 divided by 2. What will your answer come out to be? What will your answer come out to be? 24.9 minus 23.7 divided by 2. This gives you an answer of 0.6 plus minus 0.6. Perfect. Let's calculate the absolute uncertainty in the fourth row. 16.9 minus 15.3 divided by 2. Let's do it. 16.9 minus 15.3 divided by 2. This comes out to be 0.8. Perfect. Plus minus 0.8. Perfect. Let's do it for the fifth row as well. The change in time here will be 19 minus 17.6 divided by 2. That is roughly equal to 0.7. Perfect. Let's do it for the last row as well, and then we will check our answers. In the last row, we have change in time, or the absolute uncertainty in time is equals to 32.1 minus 30.9 divided by 2. This gives you an answer of 0.6. Perfect. Plus minus 0.6. Let's see this year, May, June 2023. Paper 5 variant 1. So if I take you guys to the marking scheme, here we have it. So you can see here, no, not this one. Which one do we have? This one, I guess. Yeah. You can see here that yeah, this one, my bad. So you can see here that the first absolute uncertainty 0 0.8, then 0 0.7, then 0 0.6, then 0 0.8, 0 0.7, 0 0.6. This is the same happening in the table 0 0.8, 0 0.7, 0 0.6, 0 0.8, 0 0.7, 0 0.6. Simple. Nothing complicated here. So, what is the crux or the summary of this? Whenever you are averaging out the same variable, you will calculate the absolute uncertainty using this formula. Maximum value minus minimum value divided by 2. But you have to make sure that the variable is same. And if the variables are different and you are performing addition and subtraction, then absolute uncertainties will get added up. Simple as that. Don't worry about copying. I will export this OneNote ka document and it will be uploaded as a PDF. Now, let's see this one. Yeah, let's see this one. Now, let's say you have to calculate the absolute uncertainties in a variable that is in the format of LG. Let's say you have to calculate the absolute uncertainties in LG. How will you do that? Very, very easy. You have to write down the absolute uncertainties in LG. How will you do that? Very, very easy. Very simple formula. The absolute uncertainty in LGT will be equal to what? LGT maximum minus LGT value. Perfect. So, what do I mean by that? What do I mean by that? Okay, so what is the maximum value of LG that I can have in the first row? What is the maximum value of T that I can have in the first row? Let's rephrase the question. What is the maximum value of T that I can have from this first row? The uncertainty is plus minus 1. The original number is 24. So the maximum value can be what? 25. So you can say LG 25 minus the normal value of LG, that is 24. This will give you your uncertainty. LG 25 minus LG 24. What does your answer come out to be? This comes out to be 0.017. Perfect. Now you have to give your uncertainty still one significant figure. This will become what? 0.02 plus minus 0.02. Let's apply the same thing. Okay, this remains the journal formula. This remains the journal formula. We will apply this formula to all the rows. Okay, let's apply this formula to all the rows. This is the first row getting done. Let's apply it to all the other rows. Let's apply it to row number 2. If you want to calculate the absolute uncertainty in LGT, what will be the maximum value from second row? What will be the maximum value from second row? 40, that is 33. LG 33 minus LG 32. Can you calculate the answer? Can you calculate this answer? Yes, obviously 33 minus 32. This comes out to be 0.013. If rounded off till one significant figure, this will be 0.01. Perfect. Let's do it for the third row. Absolute uncertainty in LGT is equals to LG. What will be the maximum value for the third row? 39 plus 1, that will be 40. LG 40 minus LG 39, what will your answer come out to be? Let's check that out. LG 39 and this will become 40. Your answer comes out to be 0.01. Your answer comes out to be 0.01. You don't need to round it off till one significant figure. Perfect. Let's do it for the fourth row. Absolute uncertainty in LGT is equals to what? LG 49 plus 2. That will be 51. LG 51 minus LG 49. What does this answer come out to be? LG 49 minus LG 51. This comes out to be what? This comes out to be 0.017. Simple. If I round it off till one significant figure, this will become what? 0.02. Simple. Plus minus 0.02. I think this has gotten untidy here. I think that. Let's create some space here. And let's decrease the size of all of them. Like this. Perfect. Let's do it for the fourth row. Let's do it for the fourth row. Perfect. Absolute uncertainty in LGT is equals to what? LG 64 plus 2. What will be 64 plus 2? 66. 66 minus the normal value of LG, that is 64. LG 64. What will your answer come out to be? Let's calculate it. 66 minus 64. This comes out to be 0.01. 0.013. That if rounded off, it will become 0.01. Perfect. 0.01. Perfect. Let's do it for the last row. Absolute uncertainty in LGT is equals to what? LG 76 minus LG 74. What will your answer come out to be now? 74 minus 76. This comes out to be 0.01 as well. Yeah, plus minus 0.01. Now let's see this year. This is May June 2024. Let's check the answers. Have we gotten it correct or not? May June 2024. If we see the answers here, the first row has the answer of 0.02, second 0.01, third 0.01, fourth 0.02, fifth 0.01, sixth 0.01. Let's check our answer as well. Only the first and the fourth row have 0.02. Yeah, here as well. Only the first and the fourth row have 0.02, others have 0.01. So now you have covered all the different types of uncertainties that can come in your examinations. You have literally covered all types of uncertainties that can come in your examination. Also, this might be obvious that if you have to calculate the absolute uncertainty in ln, what will you do? You will take the maximum value of ln minus the original value of ln. So this is also a given statement. I hope you have studied some basic maths. Ln and Lg will have the same basic formula. Let's further move ahead. Now, this is an obsolete thing, but this can appear in papers. So let's not take the risk. That is of adding headings to the table. This is a very obsolete concept, but this will literally take 2 minutes. So why not study it? So if you are given the velocity, let's say velocity slash ms minus 1, you have to mark the units of velocity square. What will you do? Velocity square slash meter will also get a squared, and second minus 1 will also get a square, s minus 2. Perfect. Let's say you are given the units of lambda slash 10 minus 10 raised to the power of minus 6 into meters. See, this 10 raised to the power of minus 6 is telling you what? It is telling you the power of lambda. It is telling you the power of lambda. So whenever you write 1 over lambda, this will be lambda multiplied by 10 raised to the power of 6. You can take this to the top side. 1 over lambda will now have a power of 10 raised to the power of 6. So you will write 10 raised to the power of 6 in the power here. The basic crux of telling you this is, if lambda has a power of 10 raised to the power of minus 6 and you are taking 1 over lambda, 1 over lambda will have a power of 10 raised to the power of positive 6. And the units will also inverse. If this is meter, this will be meter minus 1. Simple. Let's say you have velocity square slash meter square s minus 2. You are taking an LG of this, the units and everything will remain same. Let's say you have lambda 10 raised to the power of minus 6 into meter. If you are taking an LG of this, or let's say you are taking an LG like this, LG lambda 10 raised to the power of minus 6 slash multiplied by meters, everything will remain same. However, if you are taking an LG of 1 over lambda, then you will make the power as 10 raised to the power of 6 and the units at meter minus 1. This is just simple column heading topic. Just 2 to 3 minutes should be spent on this, not more than that, because this has become obsolete. Now let's move on to the interesting topic, that is the line of best fit and the line of worst fit. How to draw the line of best fits and how to draw the line of worst fits. So let's start with a paper, October November, paper 5 variant 1 question 2. One thing that the examiner does good here is he will already mark the axis. X axis and Y axis will already be marked. You just have to draw the lines of best fit and draw the lines of worst fit. Let me bring in the values here. So if you analyze here, this is a table that we just filled a while ago. We have the values of 1 over I and we have the values of resistance as well in the first column. Now let's study part 1 and we will see how to draw best fit lines and worst fit lines. Plot a graph of 1 over I against R. Include the error bars for 1 over I. What are error bars? We will also see that. What is a line of best fit? What is the worst fit line? We will see everything. First of all, let's start the plotting. So, when we start the plotting, first of all, an interesting thing that the examiner has already done here is he has marked the axes. So, this is something that you don't have to be worried about. Let's see the first point. The first point is x axis 1.5. That means your resistance is 1.5. Your y axis is 510. So, let's mark this point first of all. X axis 1.5 and x axis 1.5 and y axis 5150. So 1.5 in the x axis will be in the middle here, yeah, somewhere here, and 5150, right? So how will we how will we locate 5150? Very easy. On the y axis, if you see, you are going from 5000 to 5200. That is a difference of 200 in how many boxes? 10 boxes. That means one box represent a difference of 20 units. Perfect. So you have to find 5150. Perfect. Let's do that. Now you know that the middle line will be 5100. This will be 5120, this will be 5140, and this thing, let me mark it in red. This middle portion will be 5150. Perfect. So let's mark the point here. I prefer marking a dot and then encircling it like this. I prefer marking a dot and then encircling it like this. Perfect. What is your second point? Your second point is a resistance of 1.75, and on the y-axis you have 5560. Perfect. 1.75 and 5560. First of all, where will we find 1.75? Now here again you can analyze the scale on the x-axis. You are going from 1.6 to 1.8 in 10 small boxes. That is, you are covering a distance of zero point 0.2 in 10 small boxes. One small box represents a distance of 0.02. So let's say this is a 1.7. This will be 1.72. This will be 1.74. This thing will be 1.75. Perfect. This thing will be 1.75. Perfect. What is on the y-axis? On the y-axis, we have 5560. Yeah. On the y-axis, we have 5560. Please take extreme care when you are plotting the graph. So this will be your middle value, that is 5500. This will be 5520, 5540, 5560. So you have 5560 at this point, and this will be your correct point. Yeah. Let's encircle this like this. Let's encircle it like this. Perfect. Now let's move on to the third point. On the y-axis, you have 1.92. On the on the x-axis, you have 1.92. On the y-axis, you have 5810. Perfect. So first of all, let's locate 1.92 on the x-axis. This is 1.92. Perfect. Let's erase all the extra things from here. So that we know what we have plotted. And yeah, let's erase this as well. We can keep the middle value, I guess, just for reference. And here as well, you can erase all these things. You can keep the middle value just for reference. Okay. Now this is 1.92 on the x-axis. What is to be plotted on the y-axis? 5810. Perfect. So 5810 will be somewhere here. This will be 5810. Perfect. And your 1.92 is here. I guess I'm correct. Yeah. So let's mark it here. Somewhere here. The most important thing in graphs is to plot the points correctly. If you have plotted the points correctly, half of your work is done. Now let's see the fourth point. On the x-axis, you have 2.22, and on the y-axis, you have 6250. Perfect. So first of all, let's look at 2.22. 2.22 will be here. 2.22 will be here. Perfect. Okay, let's do one thing. Let's say your 2.22 is here. Perfect. 6250. Where is 6250? Let's see 6250. 6250 will be, let's zoom out further. 6250. Perfect. So if you analyze here, this will be your 6200. This will be your 6220. This will be 6240. And this middle value, let me mark it. If you see here, this will be 6220. This will be 6240. This middle value will be 6250. Perfect. So you have somewhere here 6250. Perfect. Now let's zoom out again. See, I am paying extra precaution while plotting the graphs because I know this is a difficult thing to do. And your point will be here. Yeah, I guess I'm correct. Yeah, this will be your point. Let's zoom in and make a circle here. Perfect. Let's move on to the fifth point. Let's move on to the fifth point. Oh, what have I done here? Let's move on to the fifth point. The fifth point is 2.48 and 6670. Perfect. 2.48 and 6670. So where will 2.48 lie? First of all, let's see where will 2.48 lie. 2.48 will be here. 2.48 will be here. How will you plot 6670? How will you plot 6670? Let's see that as well. 6670 will be somewhere here. This is 6620. This is 6640. This is 6660. This is 6670. 6670 is your value here. Let's zoom out a bit. Let's zoom out a bit and oh, actually, this is not on a page, na? So this sometimes get difficult to spot things. So this is your 2.48 along this line, and your 6670 is somewhere here. Chalo, let's zoom in a bit. I know that my 2.48 is on this line, and if I see here, this will be my point. Okay, so let's erase this. Your point lies somewhere here. Yeah, simple. 2.48 and 6670. This will be so easy on a graph paper. I wish I had a graph paper to show you guys. Let's move on to the last point, that is 2.72 and 6940. So 2.72 and 6940. Where will be 2.72? 2.72 will be somewhere here. Perfect. And what is your value on the y-axis? Your value on the y-axis is 6940. Perfect. So 6940 will be somewhere here. This will be 6940. Perfect. So you have 2.72, I guess. Yeah, 2.72 and 6940. So your point will be somewhere here. Yeah. These are your, you can say, 6 points. And you have to first of all draw a line of best fit using this. You have to first of all draw a line of best fit using this. Now, how will you draw a line of best fit? Let's read out some theory for line of best fit. Line of best fit is a line that levels or equals out all the points on the graph. Line of best fit is such a line that levels out all the points on the graph. And one thing that is advisable, one thing before even drawing the line of best fit, it is advisable to mark the error bars. So now let's see what are error bars. Before even marking the line of best fit, it is advisable to mark the error bars. Now what are error bars? Can you see these uncertainties? These uncertainties plotted on the graph are known as error bars. Let's see the first value of uncertainty, that is 50. And this uncertainty of 50 is in the value of what? 5150. Perfect. So what can be your maximum value here? Your maximum value here will be 5150 plus 50, that is 5200. What will be your minimum value here? Your minimum value here will be 5150 minus 50, that is 5100. So your values can range from a maximum of 5200 and a minimum of 5100. You have to display this on the graph. You have to display this on the graph. How will you do that? By drawing error bars. Your minimum value is 5100. Your maximum value is 5200. You draw two arrows at these specific points and stretch a line between them like this. Nothing complicated. Do you get it why error bars are marked? Error bars are basically marked to tell your uncertainty. Let's do it with the second point as well. Let's do it with the second point as well. In the second point, you have 5560 as your normal value. What will be your maximum value? What will be your maximum value? 5560 plus 60, that is equals to 5620. Perfect. What will be your minimum value? Your minimum value will be 5560 minus 60, that is 5500. Perfect. So you have to mark an uncertainty or an error bar in this region. Okay, let's go there. 550. Yeah. So your minimum value is 550. Perfect. So we will have a point here. Perfect. Your maximum value is 5620. So you will have a point here. Let's make an arrow here. Let's make an arrow here. Let's make a line in between. Make sure you are paying special attention to everything that you do on the graph because this carries all of the marks in question 2. So yeah, somewhat like this. Perfect. Now let's draw the error bars for the rest of the values as well. If you see here, the normal value is 5810. What will be your maximum value? What will be your maximum value here? 5810 plus 70, that is 5880. What will be your minimum value, beta? Minimum value will be 5810 minus 70, that is equals to what? 5810 minus 70, this is equals to what? 5740. Your minimum value is 5740, maximum value is 5880. Minimum value is 5740. So 5740 will lie somewhere here. Yeah, this is your 5740. Maximum value was what? 5880. So here, perfect. 5880. Yeah. So you will have an arrow like this and an arrow like this. Perfect. You can draw a line between these arrows to complete your error bar like this. Simple. Like this. Simple. Nothing complicated here. Perfect. Now, let's plot the error bar for the fourth row, I guess. Yeah. For the fourth row as well. If you see here, what will be the maximum value here? Maximum value is 6250 plus 80. Now, some students are mentally gifted. They are mentally gifted. If you can do it mentally, that's a plus point. 6330. Minimum value will be what? Minimum value will be 6250 minus 80. That comes out to be what? 6250 minus 80. This comes out to be 6170. Perfect. Minimum value is 6170. Maximum value is 6330. So let's plot it. 6170 will lie somewhere here. 6170 will lie somewhere here. Yeah, this is your minimum point. Yeah. And what was your maximum point? 6330. 6330 will lie somewhere here. 6330 will, this is the middle point. Yeah. And this will be 6320. This will be 6340. So this will be 6330. Perfect. Oh, why have I blotted this? Also, make sure you don't blot up the pencil or the graph. Don't make it too dark. Let's make this as your error bar. Perfect. Simple. Let's make it as reasonable as possible. Yeah, somewhat like this. Perfect. Now let's move on to the last error bar, I guess, right? No, two are left. Oh, when will this end? The maximum value here is 6670 plus 90. This will come out to be what? 6670 plus 90. This is 6760. What will be your minimum value? Your minimum value will be 6670 minus 90. What will this be equal to? 6670 minus 90. This will be equal to 6580. 6580. Perfect. So 6580 is your minimum value. 6580 is your minimum value. Your minimum value will be somewhere here. Yeah, somewhere here will be your minimum value. What is your maximum value? Your maximum value was what? Your maximum value was 6760. Perfect. So 6760 will be somewhere here. 6760 is somewhere here. Yeah. You draw a line between these two bars. Simple. Or two arrows, you can say. Simple as that. Now let's move on to the last error bar that we have. Last error bar that we have. See, this is just a laborious task, but it is really easy to draw. Maximum value will be 7040. Minimum value will be 6840. Simple. So let's plot it as well. 7040 and 6840. So 6840 will be somewhere here. 6840 will be somewhere here. And 7040 will be somewhere here. Yes, 7040 will be somewhere here. Let's draw a line between these two. Simple. Nothing complicated here. This is how you draw the error bars for all of the points, I think. Yeah, this is correct. Perfect. Now, once you have drawn the error bars, now you can draw the line of best fit. Line of best fit is such a line that evens out all the points. Now, what do I mean by evens out all the points? By that I mean that the number of points that are above the line of best fit will be the same that are below the line of best fit. See, this cannot be the line of best fit. This cannot be the line of best fit. Why? This cannot be the line of best fit. Why? Because only, it only has points above the line. Can you see it only has points above the line? This cannot be your line of best fit. Your line of best fit is a line that passes through maximum number of points and has equal number of points above and below. So there are two criteria for line of best fit. Listen carefully. There are two criteria for line of best fit. And a third criteria is added in paper 5 as well. The first criteria, the line of best fit should pass through maximum number of points. The second criteria is that the line of best fit should have the same number of points above as the number of points below. Perfect. The third criteria that we add in paper 5 is that the line of best fit does not go out of the error bars. The line of best fit should not go out of the error bars. Okay. So let's draw such a line. Let's draw such a line. Now, what I can do is I can Okay, so now if you see here, this is the appropriate line of best fit. You are passing through 2 points. What are those 2 points? Obviously, I will erase this, and this. You are passing through these 2 points. Perfect. And you have 2 points above. You have 2 points above. Which are the 2 points above? This one and this one. These are points above your line, and these are 2 points below your line. So you have 2 points below your line, 2 points above your line, and there are 2 points through which you are passing. Simple as that. You have drawn the line of best fit as well. You have drawn the error bar as well. Now let's come on to the worst acceptable straight line. How will you draw the worst acceptable straight line? So now there are two ways to draw the worst acceptable line. Either you can draw the shallowest acceptable line, or you can draw the steepest worst fit line. Either you can draw the shallowest worst fit line, or you can draw the steepest worst fit line. Now, first of all, let's talk about the shallowest one. You only have to draw one type of line in the examination. I am showing you two here just so that you have unlimited options. How can you draw the shallowest line possible? How can you draw the shallowest line possible? You will take the positive error bar of the first point. You will take the positive error bar of the first point and negative error bar of the last point and draw a line between them. Obviously, I will need to neaten this up. This will be your shallowest possible line. How do you draw the shallowest worst fit line or shallowest worst acceptable line? You take the positive error bar of the first point like this, and you take the negative error bar of the last point. This is how you draw the shallowest possible line or the shallowest worst fit line. This is your worst fit line. Also in the examination, make sure that you label it as well. This is your best fit line. Best fit line. Perfect. Also, you can write that this is the shallowest worst fit line. Shallowest worst fit line. How can you draw the steepest worst fit line? There is also another type of worst fit line, that is the steepest worst fit line. How can you draw that? You can also easily draw that by taking, let's take a contrasting color, let's say pink. Let's say if we can draw it with a pink, yeah, pink is visible. The steepest worst fit line can be drawn by taking the negative of the first bar, by taking the negative value or the minimum value of the first bar and taking the positive value of the last bar. Oh, I will have to restructure it a bit. 1 second. Yeah, somewhat like this, starting from here and ending at the top. Perfect. Now I prefer to keep the steepest possible line. I prefer to keep the steepest possible line, so I will be removing the blue one. Also, because blue color is not my favorite one, so I will be removing it. I will be removing it. Perfect. So, pink line or the steepest worst fit line is what I have drawn here. You can draw either one, your answers will remain same. This is the worst acceptable line or worst fit line, whatever you want to say. Worst acceptable straight line is what the examiner has mentioned, so we will also write it here. Worst acceptable line. Perfect. Now, yeah, we have marked the best fit line as well. I think best fit line की labeling is थोड़ी सी ambiguous, so what we will do is we will not label it here. Instead, we will label it at a point where both of them are clearly identifiable. This is best fit line. Perfect. This is the worst fit line. Perfect. Now let's see what the examiner is asking for next. This is what you have to draw in every paper 5. This is what you will have to do in every paper 5. There is no exemptions to that. Now let's see the next part. Let's see the next part. You have to determine the gradient and the uncertainty in the gradient. Okay, how will you do that? First of all, let's determine the gradient of the best fit line. Let's do the easier job. Let's determine the gradient of the best fit line. Now, whenever you are determining the gradient, there is just one key point that you need to remember. There is just one key point that you need to remember. You have to calculate the gradient with 2 points that cover more than 70% or at least 50% of the graph. Whenever you are calculating the gradient of the best fit line, you will take 2 points that cover at least 50% of the graph. So, which 2 points can I take here? Any points that are very, very clearly marked here. Let me see. Let me see. Yeah, maybe this one. I will prefer taking this one. This one is clearly marked. So, also, whenever you are taking points for the gradient, tell the examiner what are these points. This is 1.52 in the x-axis and this is 5200 in the y-axis. Perfect. Okay, what will be another point that I can take here? Maybe this point. Yeah, this seems good. This seems accurate and good. So this will be, uh, if I see it here, this is 3 boxes away, right? This will be 2.46 in the x-axis and in the y-axis it will be 6600. Perfect. So now you can easily calculate the gradient of the best fit line. You can easily calculate the gradient of the best fit line. I think I marked the points correctly. Yeah, let's write down the points here. Let's write down the points here. Your points are 1.52 in comma 5200, 5200, and the next point is 2.46 comma 6600. Perfect. 2.46, 6600. Can you calculate the gradient here of the best fit line? Yeah. The gradient is equals to y2, that is 6600, minus y1, that is 5200, divided by x2, 2.46 minus x1, that is 1.52. Now make sure that you include the units on the axes. Make sure that you include the units on the axes. Y-axis has no units. However, y-axis although has units but has no kilo, milli, like that. But on the x-axis, you do have such things. You have kilo ohms as your resistance. You have kilo ohms as your resistance. So you will multiply this by 10 raised to the power of 3. Let's calculate the gradient here. 6600 minus 5200 divided by 2.46 minus 1.52 into 10 raised to the power of 3. What does this answer come out to be? This is equals to 1.51. 1.51 is your answer. Simple. This is your value of the gradient. This is your value of the gradient. 1.51 is your value of the gradient. Now, sir, how to determine the number of significant figures of the gradient? How to determine the number of significant figures of the gradient? Same logic. If you can see what are the least number of significant figures in the calculated data? 3. What are the least number of significant figures in the calculated data? So you can 3, you can write your gradient till either 3 significant figures or 4 significant figures. If your calculated values have a least number of significant figures as 3, sorry, if your raw data has the least number of significant figures as 3, your calculated value, that is the gradient, will also have least number of significant figures as 3, or you can write the value till 4 significant figures. There is no harm in that. Now, how will you calculate the absolute uncertainty in your answer of gradient? How will you calculate the absolute uncertainty in your answer of gradient? Very, very easy. You will first of all calculate the gradient of the worst acceptable line. Again, take 2 points. The 2 points that I find reasonable here is this one, that is 1.6 in the x-axis, and this will be 1, 2, 3, 5, 2, 0.60. Perfect. Any other points on the worst acceptable line that are very neatly marked? Maybe this point. Maybe this one. See, I am taking the 2 points very far away from each other, at least 50% away from each other. 2.4 and this will be 2.4 and this is 6540. Perfect. So this will be 2.4 and 6540. Perfect. So now you have the points for the worst acceptable line as well. Let's calculate the gradient for the worst acceptable line as well. The 2 points are 1.6 and 5260. Perfect. And the second point on the worst acceptable line is 2.4 6540. 2.46540. Can you now calculate the gradient of the worst acceptable line? Can you now calculate the gradient of the worst acceptable line? Yeah. The gradient of worst acceptable line is 6540 minus 5260 divided by 2.4 minus 1.6, and the denominator will be multiplied by 10 raised to the power of 6. Let's calculate this answer. 6540 minus 5260 divided by 2.4 minus 1.6 whole multiplied by 10 is to the power of 3. Let's calculate the answer. This answer comes out to be what? This answer comes out to be 1.6. This answer comes out to be 1.6. Now let's start labeling things. Let's start labeling things. This is the gradient of the worst acceptable line. This is the gradient of the worst acceptable line. Perfect. And the blue one is the gradient of the best fit line. The blue one is the gradient of the best fit line. This is for the best fit line. Now, how can you calculate the uncertainty? How can you calculate the uncertainty? The difference between these two gradients is your uncertainty. Uncertainty in gradient or uncertainty in M is equals to what? 1.6. That is the gradient of the worst acceptable line minus the gradient of the worst fit line. This comes out to be 0.09 as your answer. You have your uncertainty in gradient as well. You have the actual value of gradient as well. How will you write it? 1.51 plus minus 0.09. If you, God forbid, forget this procedure, let's say कोई भूल जाता है ये procedure, so what will you do? It is written simply here. How to calculate the uncertainty in the gradient? Calculate the gradient of the best fit line, then calculate the gradient of the worst fit line. The final answer is the gradient of the best fit plus minus the gradient of the worst fit minus the gradient of the best fit line. This is the entire procedure. So here you have calculated the gradient along with its uncertainty. Make sure the uncertainty is still one significant figure, and I have told you the significant figures of gradient depends on the raw data. Simple. Now let's move on to the next part. Determine the y-intercept of the best fit line. Include the absolute uncertainty in your answer. Perfect. You have to determine the y-intercept of the best fit line and its uncertainty as well. So it's very easy. How will you calculate the y-intercept of the best fit line? Using the gradient and a point on the best fit line. You can calculate the y-intercept of the best fit line by doing what? By taking a point and a gradient of the best fit line. So let's do that. Let's first of all calculate the y-intercept of the best fit line. So y-intercept of best fit line. Let's do that. Let's calculate the y-intercept of best fit line. We know this equation of straight line y is equals to mx plus c. Perfect. Let's take any point on the best fit line. Let's take any point on the best fit line. I am doing a slight sneaky move here. I am taking the same point that I took for the gradient, that is 1.525200. I am taking the same point as I took for the gradient, 1.525200. What was my gradient for the best fit line? The gradient for the best fit line was 1.51. Let's plug in all these values here. Okay, so let's plug in the values here. In the place of y, you will place in 5200. In the place of gradient, you will put in 1.51. In the place of x, you will put in 1.52. Please remember that the values of x are in kilo ohms. So you will also multiply it by 10 raised to the power of 3 plus the y-intercept, that is c. So let's calculate the y-intercept. 5200 minus 1.51 multiplied by 1.52 into 10 raised to the power of 3. This comes out to be what? This comes out to be 2905 as your y-intercept of the best fit line. One easy thing or one thing that you can be happy about is that y-intercept के significant figures do not matter. You can give it till 3 to 4 significant figure, it doesn't matter. Let's do the same thing with the worst fit line. I have taken a point here and the gradient of the worst fit line was 1.6. So let's also write it here. The gradient was 1.6. Y is 5260. Gradient is 1.6. Value of x is also 1.6. 1 second, let me see. Yeah, it is 1.6. Very strange. 1.6 into 10 raised to the power of 3 plus c. Can you calculate the y-intercept of the worst fit line? Yeah. 5260 minus 1.6 into 1.6 into 10 raised to the power of 3. This comes out to be 2700. 2700. So how will you calculate the uncertainty now? How will you calculate the uncertainty in the y-intercept? Very easy. Y-intercept of the worst fit minus the y-intercept of the best fit. 2905 minus 2700. This comes out to be 205 as your uncertainty. How will you write your answer? How will you write your answer? Very easy once again. Very easy once again. Very easy. 1 second. How will you write your answer? Oh, let's put it here. Yeah. How will you write your answer? Your y-intercept of the best fit line is 2905 plus minus the uncertainty, that is 205. Now, according to principles, you keep the uncertainty till one significant figure. So you can do it like this: 2905 plus minus 200. Both of the answers will be marked correct. Both of the answers will be marked correct. God forbid, if you forget the procedure, how to calculate the y-intercept and its uncertainty, it is written in this PDF. Calculate the y-intercept of the best fit line, of the worst fit line, write the final answer like this. Perfect. Now let's move on to some last parts. This question that we are doing is October, November, paper 5, question 1, paper 5, variant 1 and question 2. Let's see some last parts of this question. Now we are done with the y-intercept wala part. Now let's see part D. Use your answer to A, C3 and C4 to determine the value of E, Z. Include appropriate units. Okay, we have to determine the value of E and Z. Perfect. So if you analyze what was A, what was part A? In part A, we determined that the gradient was coming out to be what? At the start of the video, we did rearrange this equation and we did calculate that the gradient was coming out to be this, the y-intercept was this. Perfect. This was part A. What is part C3? In C3, we calculated the gradient, perfect. And in C4, we calculated the y-intercept, perfect. We have to calculate the value of E and Z, include the appropriate units, perfect. So now we know that the gradient is equals to what? 3 divided by 3e minus es. Perfect. So let's write it here. The gradient is equals to 3 divided by 3e minus es. Perfect. We have to calculate e. Okay. How can we calculate e? Very easy. What was the gradient? The gradient of the best fit line was 1.51 divided by 3e minus es. What is es? 2.2 we are given here. So can we calculate the answer? I think we have written it correctly. 3e minus es was the equation, right? Yeah. So can we calculate the value of e here? Can we calculate this small little value of e here? Yeah, very easy. First of all, what will you do? 3e minus 2.2 is equals to 3 divided by 1.51. Simple. Okay. Now 3e is equals to 3 divided by 1.51 plus 2.2. Can we calculate this? 3 divided by 1.51 plus 2.2. Okay. Divided by 3. Your value of e comes out to be what? Your value of e comes out to be 1.39. Perfect. You can also give it till 3 significant figures, 2 significant figures. No like restrictions on this. Give your answer till 2 or 3 significant figures. That's the limitation here. I am giving all the answers till 3 significant figures in the last parts. Okay. Your value of e comes out to be 1.39. Perfect. Now, what will be the units of E? What will be the units of E? Let's find out. Let's find out. What was E? What was E? A student investigates an electric circuit. A power supply of electromotive force ES and negligible internal resistance is connected. Perfect. The current is measured. Perfect. It is suggested that I and R are related by this equation. E is the EMF of the cell. So if E is the EMF of the cell, what you will have the units as? The units will be volts. The units will be volts. Simple, nothing complicated. Now let's calculate Z. Let's calculate Z. We know that the y-intercept was equals to what? Y-intercept was equals to 2Z divided by 3E minus ES. So let's write it here. Let's write it here. Y-intercept was equals to what? 2z divided by 3e minus es. What was the y-intercept equal to? I guess it was 2905 multiplied by 3e minus es. What is e? 1.39 minus es is 2.2 divided by 2 is equals to your z. Can we calculate this value? Yeah, 2905 into 3 into 1.39 minus 2.2. Perfect. Divided by 2. This gives you a value of z is equals to 2861. Either you can write it till 3 significant figures. Let's write it till 3 significant figures. 2860. Perfect. Now what will be the units of z? You will again read the question. What is Z? Z is a resistor. So the units will be in ohms. Simple as that. 2860 ohms is your answer. You can check this in the marking scheme as well. If I take you to the marking scheme on the downside, you can see here the gradient is E is calculated in this manner. Perfect. We have also done it. And you can give E to either 2, 3 or 4 significant figures. It is totally your choice. Perfect. And Z determined using y-intercept. We have done that as well. The units of E are voltage. The units of Z are ohm. Simple. Let's move on to the next part. You have to determine the absolute uncertainty in E. Okay, you have to determine the absolute uncertainty in E. Now you have to pay attention. Now you have to pay a little bit of attention. If you analyze, E was calculated in which manner? Gradient is equals to 3 divided by 3E minus ES. Perfect. Can I make ES the subject here? Yeah. 3E minus ES is equals to 3 divided by the gradient. Perfect. Let's bring it to the other side. 3E is equals to 3 divided by gradient plus ES. Perfect. Divide 3 to the other side. What will happen? E is equals to 1 over gradient. Perfect. Plus ES over 3. Can you realize that E is made of two variables? One is the gradient, one is ES. Can you realize that E is made of two variables? One is the gradient, one is ES. So basically, if you have to calculate the absolute uncertainty in E, now the best way that you can calculate the absolute uncertainty in E is by first of all rearranging the equation to make E the subject here. Like this. Gradient is equals to 3 divided by 3e minus es. You multiply it to the right hand side. Rearrange the equation. E is your subject here. Now, if you put the regular values of gradient as 1.51 and E as 2.2, you will get your E key value as what? What is the actual E key value? 1.39. Now, how can you get the maximum value of E? How can you get the maximum value of E? If you put the minimum value of gradient and maximum value of ES. This will make both the fractions as maximum. So what is the minimum value of gradient? 1.51 minus 0.09. Perfect. What is the maximum value of ES? 2.2 plus 0.05 divided by 3. What will your answer come out to be? 1 divided by 1.51 minus 0.09. Perfect. Plus 2.2 plus 0.05 divided by 3. Your maximum value of E, comes out to be 1.45. This is your maximum value of E. This is E max. This is normal E. Can you calculate the difference between the two? The difference between the two will be your absolute uncertainty in E. E max minus the original value of E 1.45 minus 1.39 gives you an answer of 0.06 volts as your absolute uncertainty in E. Simple as that, nothing complicated here. Probably the easiest question of the lot. You have to take the equation from the top, that is 3E minus ES. Let me write this here. 3E minus ES is equals to current into what? Current into 3R plus 2Z. 3R plus 2Z. Perfect. So what you can do is you can say 3E minus ES, perfect, divided by the current minus 2Z, perfect, is equals to 3R, perfect. Divide 3 with all of them. 3E minus ES divided by 3I minus 2Z over 3 is equals to your R. How will you calculate the value of R? Now just substitute the values. What is the value of E? 1.39. 3 into 1.39 minus ES, that is 2.2, divided by 3 into the value of current, that is 250 into 10 raised to the power of minus 6. Why? Because microampere. Minus 2 into Z. What is the value of Z? The value of Z is 2860. 2860 divided by 3. Let's calculate this answer. 3 into 1.39, perfect, minus 2.2 divided by 3 into 250 into 10 raised to the power of minus 6, perfect, minus minus, oh, why have I erased the fraction? My brain has started to freeze at the end of the video. 3.9 minus 2.2 divided by 3 into 250 into 10 raised to the power of minus 6 and minus the answer, that is 2 into 2860, perfect, divided by 3. Your answer comes out to be 720 ohms as your answer. Perfect. Let's see. Yeah, here the examiner has done the same thing. 3 into E minus 2.2 minus 2 into Z divided by 3, and in the denominator as well he has divided it by 3. So yeah, this is the method that we have done. Perfectly correct. So I have done a complete paper as well. I have told you how to solve for uncertainties as well, for significant figures as well, how to draw a graph, how to draw the line of best fits, worst fits, how to calculate the uncertainties in gradients and y-intercepts. The document is uploaded in the description below. Make sure you watch the video again if anything is confusing, and you can ask any ambiguities in the comments as well. Thank you for watching.